Let me pull it up, I guess. Whoops, that's not what I want. I think it is. Number 9 is really just on there, so when I don't assign it, you feel like I'm a compassionate person. Okay, so we're doing this one. And here's where we are so far. So we have done the 2 rigid bodies, and our system of equations is this. Negative 0.482 F12x plus 0.575 F12y minus 15 alpha 1 is equal to 399.99. And then negative F12x minus 20A2x is equal to 0. And then negative F12y plus RC minus 20A2y is equal to 196.2. And then the fourth and last equation that we have so far is 0.575 RC minus 3.75 alpha 2 is equal to 0. And so here is our system so far. This is 4 equations. And for unknowns, we have F12, that's a 2D vector. A2 is a 2D vector, so that's 4. Then alpha 1 is 5. Alpha 2 is 6. And RC is 7. So our variables are F12, A2, alpha 1, alpha 2. Those are both just scalars. And then RC. 1, 2, 3, 4, 5, 6, 7. And now we have to deal with the constraints. How did I letter these? I called this member 1, member 2, and then I called this A, B, and C. I think maybe it was Joe who asked last time. Someone asked last time. What are the constraints that we're going to use here? We're going to use a constraint at B that says the 2 members don't fly apart there, so their accelerations are the same. And we're going to use a constraint at C that says that pin can't move up and down, so it can't accelerate up and down. What about A? There's a pin there. Why don't we use a constraint saying that that acceleration is 0? Well, essentially we do, because, like, for example, when we're calculating the acceleration at B, we're not using relative motion because we're assuming that that joint at A is fixed, okay? And so, so everything that we've done so far, including the moment equation and everything, has been assuming that there's no acceleration at that point A. And so that's why we don't have to do it again as a constraint. We've already accounted for that. Okay, so we're going to start with the constraint at B. And I'm going to do it for each member. And so according to member 1, the constraint at B, these are each 1.5 meters long. So this is equal to alpha cross R plus omega cross R. Is there anyone who doesn't recognize this equation? You should recognize this by now. This is a really key equation. So alpha is 0, 0, alpha 1. We don't know what that is, but we've already used that variable. Omega is 0, so this part goes away. And R is 0.75 times the cosine and sine of 40 degrees. And that looks like that is 0.575, 0.482. So the acceleration at B, according to member 1, is 0, 0, alpha 1 crossed with 0.575, 0.482, 0. X is negative 0.482 alpha 1. Y is positive 0.575 alpha 1. Z is 0. We can leave that off or put it in. This is member 1. And now we'll go to member 2. There's no fixed point on member 2, so we're going to have to use relative motion. And so the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass plus the acceleration of the center of mass relative to the ground. We already have a name for this. This is our A2. This is the watermelon equation, but it's going to simplify even more than that in this case. So the acceleration of B relative to the center of mass is equal to alpha cross R plus omega cross quantity omega cross R. And what are these values? The alpha vector is 0, 0, alpha 2. The omega vector is 0, so this whole thing goes away. And then the R vector in this case, so I think it's a good idea whenever you're writing down R or writing down rho, repeat the definition of it in your head. You know, you really want that to be ingrained. In the next section, more than in anything else, you're really going to see why, because if you're not thinking of these as definitions, it's going to mess with your head, okay, like what these vectors are. So that R vector goes from the center of the circular or spherical motion to the point that you care about. The center of the circular or spherical motion, this is relative to the center of mass. So that is the center of mass, okay? The point we care about is also the center of mass in this case. And so this r vector is 0. And so there's no acceleration of b relative to the center of mass. And so that says that the acceleration of b relative to the ground is just equal to a2. And then once you see that, then you're like, okay, obviously, because we're talking about what's the acceleration of the center of mass, and we already have an expression for it according to member 2. And so now the constraint says negative 0.482 alpha 1, 0.575 alpha 1 is equal to a2x, a2y. And so our fifth equation says 0.482 alpha 1 plus a2x is equal to 0.
Is that supposed to be negative?
Yeah, I just made them both positive. I don't know why I did that, but I just like the look of positive, I guess. But yes, you're right. It'll work either way because that's you can replace any equation with a linear multiple of other equations. So multiplying it all by -1 is a linear multiple, And this one says 0.575 alpha 1 minus a2y is equal to 0. So this is equation 5 star and equation 6 star. Any questions about that? And now the last constraint is the constraint c. And so we're going to come up with an expression for the acceleration of c in terms of variables we already have. And then we're going to set the y component equal to 0 because this is free to slide along x, but it's not free to move along y. So this is the constraint at c. So the acceleration of c relative to the ground is equal to the acceleration of c relative to the center of mass of body 2 plus the acceleration of the center of mass of body 2 relative to the ground. This is the variable a2. And this is the watermelon equation. The acceleration of c relative to the center of mass is alpha cross r, all ripe watermelons will rot. Alpha is 0, 0, alpha 2. Omega is 0, so this part goes away. And the r vector is from the center of the circular motion to the point we care about. Anytime you're doing something relative to something else, the center of your circular motion is what you're relative to. So in this case, we want a vector that goes from the center of mass to the point C. Okay, and so that is 0.575 negative 0.482. So the acceleration of c relative to the center of mass is 0, 0, alpha 2 crossed with 0.575, negative 0.482, 0. And that is 0.482 alpha 2, 0.575 alpha 2, 0. So the acceleration of c relative to the ground is 0.482 alpha 2, 0.575 alpha 2. I'll just leave off the z's now. Plus a2x, a2y. Now for the constraint, we want to set the y component of this equal to 0. So our last equation says 0.575 alpha 2 plus a2y is equal to 0. And that's equation 7 star.
Why isn't it 20 times A2X?
This is, so when you do the rigid body analysis, you're using Newton's laws. So all your equations are coming from Newton's laws. Once you get to the constraints, you're not using any kind of kinetics anymore at all. All you're doing is putting restrictions on the combinations of possible accelerations. And so all you're doing is representing accelerations and setting them equal to each other, equal to 0, that kind of stuff. And so the mass never comes into it anymore. Constraint equations will never have forces or mass in them. Anybody want to see this? Want to see the solutions to this, or is the flow of these problems good? Anybody want to see me go through the matrix?
I'm just
Yeah.
quick on the question. So if you go back up to the picture, if this slot was like vertical, let's say,
Yeah,
then the x would be equal. You'd set the
That's
x
right.
one equal to 0.
that's right.
Okay. So it's whatever direction it's going, you set down.
It's always perpendicular to the slot is equal to 0. Because, you know, there's a million things you could do to this to make it accelerate horizontally, you know?
Yeah.
But there's nothing you could do to this to make that pin accelerate vertically. And that's what we're doing. We're saying that slot, no matter what you do, doesn't allow this pin to move vertically.
Okay.
And I'm going to erase this so it doesn't cause confusion in your notes. But what if this slot was like, this? Okay, let's say this angle is 30 degrees. How would we do that? So what we would do is we would say that this thing can't have any component of acceleration perpendicular to that angled slot I just drew. Okay, so if here's the horizontal, here's the slot, perpendicular to that is like this, and we want the component of this acceleration vector that's parallel to that green vector to be equal to 0. So how would we do that? Well, we'd come up with a unit vector representing that green vector. This angle, I'm running out of colors, but this angle is 30 plus 90, so 120 degrees. And so a unit vector would be cosine of 120, sine of 120. Which I guess would be negative 0.5 positive 0.866. And then we take the dot product of this with the acceleration vector and set it equal to 0. Remember, the dot product of two vectors gives you a scalar. So we'd have 0.482 alpha 2 plus a2x 0.575 alpha 2 plus a2y dotted with this unit vector set it equal to 0. And so that says negative 0.5 times 0.482 alpha 2 plus a2x plus 0.866 times 0.575 alpha 2 plus a2y. All of this is equal to 0. Multiply it all out. It's just a single equation, but that would be our final constraint equation in the case of an angled. So what you're always just doing, no matter what the angle is of that slot, is you're saying this thing can't accelerate perpendicular to the slot. The slot prevents that. Okay? You don't have to know this well enough to do it on a test. I'm not going to put angled things on a test, but you should try to know it well enough that if someone doesn't know what to do in a case like that, you can convincingly, make them feel stupid about it. That's a big part of advancing as an engineer. Okay, I'm deleting this. The last example I want to do with linkages is a 4-bar linkage. This is something that comes up in a lot of industries, a lot of types of machines. It comes up in biomechanics. And the way that you do a problem like this is exactly the same as any other linkage problem. We've done almost exclusively 3-member bodies, just to cut down on the number of equations and stuff. But a 4-bar linkage, I'm going to draw a simple one. So these are connected by pins. And let's give some angles. Let's say this is 50 degrees. This is 50 degrees. Let's say we'll make all of this sort of the same lengths. So this is 1 meter. And I'll name these members 1, 2, 3, and the joints A, B, C, D. And the only external load we're going to apply is a couple on this body, on member 3. And let's say that's 100 Newton meters. And let's say member 1, 2, and 3 each have lengths of half a meter. These are masses. So let's say these are all 1 kilogram. And let's say the lengths are all half a meter. And let's say that what we want is the acceleration at b. Okay, so one of the things that 4-bar linkages do that's useful is as they move, well, they're defined by a single degree of freedom. Okay, so which is, once I give the dimensions of all this stuff, one single angle of these tells you the configuration of everything. And one of the things that's useful for is every one of these points traces out a curve, a defined curve. Okay, so that's something you can take advantage of. 4-bar linkages are used in engines. A human knee approximates a 4-bar linkage pretty accurately with there's sort of a complicated configuration of ligaments and things in the knee that keep it moving a certain way, and they kind of act like a 4-bar linkage. And so this is something, you should recognize that term, and we'll go through a calculation. Question?
I don't know if this matters, but can the lengths of each bar be half a meter?
Yeah, you could change the lengths, and it just changes the way the curves act.
Won't those bars not be able to be parallel if they're spaced a meter apart?
It's a parallelogram with every side 1 kilogram, half a meter. Oh, 1 meter, right. Thank you. I meant this to be half a meter. All those distances are the same.
Would you still be able to do the math and it just
Yeah.
wouldn't make any sense?
That's right. It does make sense. It would make perfect sense. It just wouldn't stay a parallelogram like this. The way I have it, it's going to stay a parallelogram. Let's say, like always with linkages, you have to know what the angular velocities are. Let's say that the angular velocities at this instant are all equal to 0. And, well, if you count the bars, you see 3 bars, and that might throw you off a little, but the ground acts as the 4th bar, and that's often the case with these. So what you really have is kind of 4 defined distances between things. Okay, before we go into this, let's think about the number of equations that we expect to get from this. So member 1, does it have a fixed point? Yep. So with a fixed point, is there going to be Newton's second law in our calculations? No. So how many equations are we going to get out of that? 1. Okay. So now moving on to member 2, we have 1 equation. Does member 2 have a fixed point? No. So we do need Newton's second law. And so how many equations are we going to get for member 2? 3. So now we have a total of 4. Does member 3 have a fixed point? Yes. So how many equations? 1. So we have a total of 5. And now we have to think about the constraints. So at B, we don't have to worry about the constraints at A and D, at A or D, because those are already built into our equations. We do have to worry about the constraints at the 2 joints that can move. So at B, we're going to say that according to member 1 and according to member 2, the acceleration at B has to match. Okay, so how many equations do we get from that constraint? 2. So now we're at 7. And then at member C, the same thing, 2 more equations. And so we have 9 total equations. Okay, let's think about variables and make sure it makes sense. This can be a little tricky to think about, but try to walk you through it. So we're expecting to have 9 variables show up in the equations, okay? On this first one, if you think about a free body diagram, we'd have a reaction force RA, full vector. And then we'd have a reaction force F12 up here. And then we're not using Newton's second law, so we'd have an alpha 1, but no A1 vector. Okay? So at your first thought, you think 1, 2, 3, 4, 5 variables, but 2 of those variables are not going to show up in Newton's laws. Can you think which 2 those are?
Reactions.
The reactions at A are not going to show up because we're not using Newton's second law, and that's the about point. So they don't produce a moment since they're at the about point, you know? And so we start out with 1 equation and 3 variables. Now go over to this one. There's a force here, F21, which is negative F12. That's a pair of variables we've already considered. There's a F23, there's an alpha 2, and there's a A2 vector. Okay, so that's 1, 2, 3, 4, 5 new variables. So now we have 4 equations and 8 variables. Okay, are you with me on that? Does that seem right?
Should still be 9, right?
9?
He hasn't gotten to the last one.
Oh, I'm sorry.
Yeah, right.
He's going
So,
around.
right, I'm going around. So we're at 8 variables. And now we'll go to the last one. Again, there's, F32, but we've already named that one. That's already negative F23, so that's no new variables. This RD, that's a force vector that we don't know, but it doesn't show up in our equations because we're not using Newton's second law. So the only new variable is alpha 3. Bless you.
Thank you.
And so that's our 9th variable. And either way you think of it, we come up with a total of 9 variables for 9 equations. Bless you. Okay, no more. No more sneezing, please. We have to concentrate. I know everybody loves sneezing, but come on. All right, so let's do it. Oh no, 50% screen rate. Sometimes you have to get worse before you get better. What happened over there? Is it a problem with the input terminal? That's what I did do.
That was that one. That was the right screen.
Yeah, it's a different color. So well,
Maybe it's with the
can anyone?
itself.
Is there anyone who can't see that screen who's sitting over here? I don't know what else to do here except restart the whole system. Can you guys follow over here? Okay.
We can do it if we need to.
Okay, so member 1. There's a fixed point, and so the moment of inertia is going to be taken around A, and so that's 1/12 times the mass times the length squared, plus we have to use the parallel axis theorem, so this is 1 times 0.25 squared. And that is 0.083 repeating. Now, free body diagram. We have RA here, a weight force down of 9.81, and a force vector here of F12. Our about point is down here at A. So I'll start with RA. Rho vector is 0. Force is RAX, RAY. Next, I'll do the weight. The rho vector, this is 50 degrees, 0.25. So I got negative 0.161, positive 0.192. The force vector is 0, negative 9.81. And that is 1.576. And then the last one is the force F12. The rho vector is negative 0.321, positive 0.383. The force is F12x, F12y. The cross product is negative 0.321 F12y minus 0.383 F12x. And the first equation, this has a fixed point. We're not using Newton's second law. So the first equation is from rotational Newton's second law. And it says negative 0.383 F12x minus 0.321 F12y minus 0.083 repeating alpha 1 is equal to negative 1.576. Any questions about that?
But you're taking the angle of at 50, right? To find FG and F12.
Yeah.
Or
The length, the distance from our about point to where the weight is 0.25 because the whole thing is 0.5. So yeah, I used if I think of this as the positive
this
x,
angle right here.
yeah, it would be
So
like
180 minus
130
Yeah.
degrees, cosine and sine of 130. Now we're going to go to member 2. Does member 2 have a fixed point?
No.
No fixed. And so the about point is the center of mass. So the moment of inertia is just 1/12 times 1 times 0.5 squared. Which is 0.02083 repeating. Free body diagram. Okay, so over here we have the force on 2 by 1, but I'm going to call it negative F12. Weight force down that way of 9.81. And then over here we have the force on 2 by 3. For the people who've done internal loads and stuff, you're pretty used to calculating this kind of thing without doing a table, but it never hurts to do a table when you're doing rigid body kinetics. So I'll do it here. One of the nice things I think about filling out a table is just you have all this, you have a record of everything you've done, so it's a lot easier to find mistakes, you know. If you do stuff in your head by just thinking like, okay, that's going to make it rotate this way and whatever, it's just hard to go back and check without just redoing all the work. Okay, the about point is the center of mass, so I'll start there. Oh, freeze. Okay, so the weight force, rho vector is 0, 0. The force is 0, negative 9.81. Cross product is 0. Then negative F12. The rho vector is negative 0.250. The force is negative F12x, negative F12y. Cross product is 0.25 F12y. F23, the rho vector is positive 0.250. Force is F23x, F23y. Cross product is 0.25 F23y. There's no fixed point, so we need Newton's second law. And that says negative F12x minus F12y plus F23x, F23y plus 0, negative 9.81 is equal to 1 times A2x, A2y. And I'll write that out as our next two equations. Negative F12x plus F23x minus A2x is equal to 0. And minus F12y plus F23y minus A2y is equal to 9.81. That's our second and third equations. And then the moment equation says 0.5 F12y plus 0.5 F23y minus 0.02083 repeating times alpha 2 is equal to 0. Any questions about that?
I think I missed, why is it 0.51 It's from the center of mass to.
Yeah, I just wrote it down wrong. Thank you. That's why you fill out the table so you don't do stuff like that. Didn't work. Any other questions about that one? Okay, and then do we have time for the last one? Maybe. Let's see. So now we're on member 3. Over here we have a force RC. What am I doing? I'm getting ahead of myself. Is there a fixed point on this one? And so we have to use the moment of inertia about that pin with the floor. That's going to all come out to be the same as it was with member 1. So that is 0.083 repeating kilogram meter squared. And actually, let's just stop there. We'll finish next time. Why don't, I think what I'm going to do, we're out of linkage problems anyways, so I think what I'm going to do for an assignment is have you finish this, and then I'll go through it in class. You can check your notes against what I do, if you know. So I think that's my plan. And then once we're done with this, which might be by the end of the class on Friday, we'll get into the next topic, which is the coolest topic, I think, in this class. And the most mind-bending one, we're going to start talking about doing calculations in rotating coordinate systems. Yeah, it's going to be good.